Okay, so we are into our last lesson now, 7.7, problems involving exponential decay. And in the previous lesson, we looked at exponential growth. So we are just looking at just the other type of application problems. And this is when we are dealing with decreasing functions, okay? So decaying is another way of saying decreasing. And generally speaking, what that looks like is your function is getting lower and lower as you're reading it left to right. Okay, so just as I started the previous lesson, as you're reading your x values, all right, as x values are increasing, so again, reading left to right, your y's are decreasing. Okay, so in exponential decaying problems, what you expect is that as if you created your table of values, all right, I'm jumping ahead here, but if you create your table of values, and as these numbers get bigger, as you increase here, what you would expect is that the y values here decrease, okay? So they get smaller and smaller. That's what an exponential decaying problem is. So in this first paragraph, all right, what we're really saying is that in exponential decaying problems, you can use this formula, all right? And what this formula is, it's saying that if I ask you to calculate the future value, okay, some final amount, well, that's what the function is giving you. That's what this is right here. This is your final amount, right? And then on the right-hand side of the equal sign, well, this is what you're starting with. And then this is your rate, okay? This is like the rate or the ratio. The ratio. And it's saying like, let's say you had 100 milligrams of something and you had 30% of it left over. Well, the rate or the ratio would be like 30%, right? You'd say, okay, you have 30% of it. But you can't just multiply by 30%. You multiply by 0.3. And you'd have 30 milligrams left over. So that's what this portion is saying. It's like what rate is being applied. But if I said that you do this 30% a certain number of times, well, that's where this exponent comes in. That's the how many times are you taking 30% of it, or whatever your scenario is, okay? So you have the initial, you have your rate, and then you have this exponent. How many times are you doing the decaying, or how long is, or in this case, the number of growth periods. Now there's one other variable, okay? When you deal with half-life problems, which are super common in this, all right, I'm just going to expand on that formula just a bit, okay? So let's pretty much copy it down as you see it. So P of n is P of naught 1 minus R, but specifically in half-life problems, this 1 minus R has a value of half, okay, because you're taking half of whatever your initial amount is. It is still being put to the power of n. Now, the thing that I want to add is this variable on the bottom right here, okay, this variable x. And what this x is the problems will usually say it has a half-life of X amount of days or years or something. This is the half-life time, okay? So if it ever says half-life time, that's where you put that. It is your exponent divided by that amount, all right? So that will make sense as we get into this first example here, okay? So living organisms contain both carbon-12, which does not decay, and radioactive carbon-14, all right? So when you hear something called carbon dating, when you think about fossils and everything like that, that's what that means. You're actually looking at carbon-14. And the reason carbon-14 is special is because we know that it decreases exponentially, but specifically, we know it decreases half. All right, half of it is remaining after 5,730 years. Okay, I know it seems like crazy, but we're talking about like fossils, like millions of years old. And notice this 5,7, the half-life time. All right, that's what it's saying. The half-life of about 5,730 years. Look where that number is on our model. I gave us an equation here, and notice how similar it looks up top here. Here, I told you had a half. Here's your half. And then this is where that 5,730 goes. It goes on the bottom of the exponent, okay? Yeah, up here, this has n, but that's because right here, this is t, right? So instead of it being p of n, it's now p of t. So that's why t is up here. But the main thing is notice the half-life time. Okay? So in this case, x is 5730. So you use this model, this P of T represents the percent of carbon remaining, the future amount after T number of years, okay? So in this first problem here, bristlecone pine fossils found in western United States show an age of about 6,000 years using carbon dating. What percent of the original carbon-14 remains in the fossil? So after 6,000 years, what percent is remaining? So this is saying when T is 6,000, what is P of T? So if we just use our P of T formula, our percent of carbon remaining, well, we have 100, and that is multiplying by half, and you're putting it to the power of t, all right, t, and you're dividing it by its half-life time, 5,730. But now the problem is saying, what is P of T when T is 6,000? So we substitute 6,000 for the T right up top here, 6,000, and that is being divided by 5730. So your calculator might bug out if you try and put half to the exponent of this. So simplify this first. Simplify this. All right. So if we write our next line, this is going to be 100 multiplied by half. And when I say simplify, literally take 6,000 on your calculator, divide that by 5,730. All right. And I am going to get roughly 1.04712, okay? But don't go what you want to do on your calculator is instead go to evaluate this portion right here, just so you don't avoid rounding errors, go 1/2 to the power of answer. That way it is an unrounded amount, okay? So you don't actually have to write this number, you're using answer. So I go 1/2 or 0.5 to the power of answer, and then I multiply that by 100, and I get 48.39. All right, P at 6,000 equals 48.39, but what does that 48.39 represent? Well, P of T represents the percent. So this right here is a percentage. It's a percentage. So therefore, after 6,000 years, 48.39% carbon 14 remains. Right? So this is what I mean by carbon dating, by the way, if you're just interested. It's like if you had some fossil that you found, and if you found that, I don't know, there was only like 3% of it remaining of carbon 14, well, then you'd be able to figure out, because you would know this number, you would know what this is equal to, so your only unknown would be the T up here, and you'd be able to tell how old that fossil is. You'd be able to say, oh, this is from millions of years ago, okay? So that's actually what we're going to be doing in this part B right here. Sediments deposited by glaciers during the last ice age covered and buried layers of peat. Carbon dating, right, that word, carbon dating, shows about 25% of the original carbon-14 remaining in the peat. Estimate the age of the glacial deposits to the nearest 100 years. All right, so take your carbon dating, your P of T formula. So we're still going to be using P of T, which is 100, oh sorry, 100, not 1,000, 100 multiplied by 1,000, oh sorry, 100 multiplied by half, I'm sorry, to the power of T over 5730. 5730. Okay. So what we are doing is we're trying to estimate, okay, how old this is. So we are just going to be substituting in different values of T into this T up here. And we'll do that 1, 2, 3, 4, 5 times, okay? And what we want to find is when any one of these roughly equal 25%, okay? Because when we find a T value that gives us 25%, then we know how old it is. So what this problem is saying is find the T when P of T equals 25%. That's what this problem is asking us to do, okay? So let's calculate it. In this first one right here, you're calculating P measured at 12,000, okay? So just to show this math for the first one right here, all right, P at 12,000 is 100, 1/2 to the 12,000 divided by 5730. So again, simplify your exponent first. So 12,000, 1, 2, 3, divide that by 5730. I hit equals on my calculator. And then I go 0.5 to the power of answer. And then, so right now I have 100 multiplying by whatever my answer was, 0.2342. And then I multiply that by 100. And I get 23.42%. Okay, so that's not 25, okay? So this right here is 23.42%. So try that for each one, okay? So I'm going to pause the video for a second just so you don't have to see me do the math. Okay, so I'm back and there is our chart filled in. Just so you don't have to watch me plug in the calculator, because at the end of the day, this is just calculator work. All right, so just so you're seeing it one other time, how I got this number right here. Again, it's because I took my formula, P, and I was measuring it at 11,200. So I took my 100. I was then multiplying that by a half, which was put to the exponent of 11,200, the number I'm evaluating at. And I divided it by 5730. So I did this exponent first. So I got 100, 1/2, and then I did 11,200 divided by 5730. So I had 1.954 up top here. And then I went 0.5 or 1/2 to that exponent. So then I got 0.5 to the exponent of that. And that gave me 100 times 0.2580. And then when I multiply by 100, I get 25.80%, okay? And that's where that number came from. And that's what I did for each one of the other ones while the video was paused. So the question was saying, well, what time, all right, how many years was it past when the percent was, how many years went by that 25% is remaining? Well, we can see that after 11,600 years, there was 24.58%. And after 11,400, there was 25.81%. So that means sometime in between here, all right, you had 25% remaining. So therefore, some time between 11,600 years, sometime between 11,600 and 11,400 years All right, that's how many years have passed such that 25% is remaining. All right, so it's some time. And there's a graph here on the side because you can do this graphically. I don't think there is much merit to that, but actually you can see this question is taken directly from the textbook, right? And this question in the textbook, they have the graph done, and you can see they do the same thing. They do an estimate right here, and they say, oh, okay, and they conclude that pretty much you get the same answer, right? So we just got the answer from our table of values, but yes, if you graph this, you can also do the same thing and just get an estimate, all right? But for the interest of time and not making this video super long, I'm just going to answer it by looking at a table of values. So let's move on to example 2. A hospital uses cobalt 60 in its radiotherapy treatment for cancer patients. Cobalt 60 has a half-life of 5.2 years. Okay, so there you go. There's that half-life time, right? So this is that x equals 5.2, right? Like that number that you're putting on the bottom of the exponent. This means that every 5.2 years, 50% of the original sample, all right? So 50%, right? Like half-life. You can also get that from the half-life problem. This tells you that your rate or your base is 1/2, right? Your exponent is 1/2. So this means that every 5.2 years, 50% of the original sample of cobalt 60 has decayed. The hospital has 80 grams of cobalt 60. It requires at least 64 milligrams for the therapy machine to provide an effective amount of radiation. Determine an equation that models this situation. Okay, so the hospital has this amount, right? So what this is your initial amount. This is your initial amount. So that's that whole P of 0, right? So determine an equation that models the situation. Well, we have some future amount, okay, some future amount, P of n in our case, and that 80 milligrams that it has, all right, this is P naught, is being halved, and the rate at it's being halved, right, is divided by this 5.2 here. 5.2, okay? So n in this case is how long, how many times, how long this thing is being taken or required. How many years, right? Like n is the period or time passed. And P of n is the future amount. So use the equation to determine how often the staff must replace the cobalt in their machine. Okay, so if we need at least 64, so replace the machine, pretty much when, all right, or we are looking for n, when P of n equals 64 milligrams, okay? Because it says that when they have at least 64 milligrams, they're okay. But if they have any less than that, then they can't do it, right? So what we are looking for is 64 equals 80, 1/2 to the n, and divide that by 5.2. Okay, so what you need to do is you are trying to guess and check, okay? So it's a trial and error. Trial and error problem where you just choose values for n, okay? And what you are trying to see is when you can get this left-hand side, the right-hand side, when you can get this hand side right here to roughly equal 64. So let's try it, okay? So I'm just going to choose a value, hypothetically, when n is 1, just to get a benchmark of where we are. So I take 80, and I say 1/2 to the power of 1 divided by 5.2. And let's see what I get. Let's see what happens if I only let 1 day pass, okay, or 1 year pass. So 0.5 to the power of 1 divided by 5.2 equals, times that by 80. I get 70. Okay, so after 1 year, because n is measured in years, n is the time pass period, or time passed in years, because the problem is saying in years right here. So after 1 year, we're still good. Let's try it again. Let's do n of 2. Let's see what happens. So 80, 1/2, 2 to the power of 5.2. Okay, what do we get? So 2 divided by 5.2, then go 0.5 to the power of answer, times that by 80. Okay, so in this problem right here, I got 61.2, well, it doesn't matter, but 61.28, right? And that's milligrams. So this one did not work, okay? So what you can conclude, all right, you can keep trying this, and let's do it one more to maybe get another specific. Let's try 1.5, so n being 1.5. So what this means is a year and a half, right? Or a year and 6 months. If we do that, we have 80 times 1/2 to the 1.5 over 5.2. Let's see what we get. So 0.5 to the power of 1.5 divided by 5.2 times that by 80. I get 65.5. Okay, so clearly we think about a scale, right? Like what we just found, milligrams. So this one is good, okay? And you could keep repeating this process, right? So I think 3 attempts is enough I'll ever require on a test, all right? Just so I understand what you have found. But if we think about like when it is good to when it is bad, and we draw like our time scale here. So after 1 year, we were good. And then another 6 months passed, okay, so 6 months went by, and we got to a year and a half, we were still good. But then we got to 2 years, and we were bad, right? 2 years, we were bad. So that means sometime, there was some month in here that they had to replace it, okay? Because you're still good here, but you're bad here, all right? So therefore, some time between, sometime after 1 year and 6 months, okay? Sometime after 1 year and 6 months, they need to replace it. And you can keep doing that trial and error process over and over again until you get exactly the right amount, okay? But again, 3 attempts is enough to give me an estimate that you know what you're doing, okay? To try to find the right amount. So part C, how much of the original sample will there be after 1 year? Well, that's our attempt right here. This is after 1 year. Okay, this is after 1 year. So that's part C. So we already did the math, okay? So after 1 year, there will be 70 milligrams left over. Example 3. When a basketball is correctly inflated, it rebounds to approximately 60% of the height from which it was dropped. Correctly inflated basketball is dropped from a height of 2.4 meters and continues to bounce, each time rebounding 60% of its previous height. The rebound height of the basketball, h, can be modeled by the equation h equals, really this actually should say h of n, because the variable appears n. So h of n is 2.4, 0.6 to the power of n, where n is the number of rebounds. Explain the meaning of 2.4 and 0.6 in this equation. Okay, well, I mean, look where these numbers are coming from. Where did 2.4 and 0.6 come from when you read the question? And a correctly inflated basketball is dropped from a height of 2.4. So dropped from, okay, this whole thing. This is when time is 0 or initial. And if you think about all of your problems, right, when we set up these things right here, look, 80 grams, initial. That's at 80 right there. If we go back up to even the beginning of the lesson, right, very beginning, whenever you have these problems, always initial right here multiplied by your rate. Okay, so let's go back down to the problem we're dealing with. Notice right here, you have this formula, 2.4. This is your initial. This is the initial height. And then the thing that you're multiplying in your exponent right here, this is the percent or the rate of decrease. Okay, because it's saying 60% is remaining. So explain the meaning of 2.4 and 0.6. Well, 2.4 is the initial height. And 0.6 is the 60% rate of decrease. Because it's saying 60, every time the ball bounces, you have a rate of decrease of 60%. It has 60% of the initial height of what it originally was at. So part B is saying then, use the equation to determine the rebound height of the basketball after 5 rebounds. So it's looking for the rebound height. So it's looking for h, or h of n, and it's telling you after 5 rebounds. So here, n is 5. So just take your formula, and you're calculating h of n. H of n is 2.4 multiplying by 0.6, and in this case, we're putting it to the power of 5. So 0.6 to the power of 5 times that by 2.4, and it roughly equals, doesn't say to round it to anything, so I'm going to say round to 2 decimal places, 0.18 meters. And is it measured in meters? Yeah, meters. What is the domain and range for the function modeling the rebound height of the basketball? Okay, so in general, I told you the domain for exponentials is x belongs to real numbers, right? But if we think about the context of this problem, right? You know, you have some basketball and it's gonna bounce and bounce and bounce like that, right? So if we think about this problem particularly, if you look at the height of the basketball over time, right? Well, what is the domain? Well, the domain in this case is modeling n, right? So n is measuring the number of bounces. Okay? So in this case, your domain is that n belongs to real numbers, right? But you have, in this case, n has to be greater or equal to 0. Greater or equal to 0. That's where your domain is, right? Because you can have 0 bounces, and then you can just have however many the ball bounces for. It just needs to be bigger than 0. And the range in this problem, the range is the height of the ball. Right? So in this case, your range and the variable we're measuring is actually h, h belongs to real numbers. Well, in this case, if you think about what you're measuring on your graph, you are starting your initial at 0 bounces, you're at 2.4. And then the ball bounces and the height decreases as it bounces at an exponential decay. So 2.4 is your maximum and 0 is your minimum. So you are between 0 less than y less than or equal to 2.4. And the reason I didn't put a equal sign here is this is your asymptote. Okay, remember, exponentials have an asymptote at y at 0. So I shouldn't have put y here because we're measuring the variable h. That's your asymptote. So not equal. Not equal. Okay. And that it concludes the last lesson, all right, for this unit. So there is our homework, and we'll do that in class. Bye for now.